We finished last week with some examples I showed you on my laptop with addresses. For example, I mentioned two types of addresses, a hardware address and an IP address. I think you all, and maybe over the last week, your homework task was to look at your addresses on your computer. Your phone will have one, your tablet, your laptop, your PC at home. You should be able to find the hardware address and the IP address on those devices. Today we'll explain them in a bit more detail. And we'll do so by looking at what happens if we want to connect two different, say, LANs, two different local area networks together. So think about before the internet was popular, different organisations had their own internal networks. So a university, and I'll draw it as a cloud to represent there are some computers, say inside SIT or inside Thammasat University, many computers connected together on their local area network, their LAN. So the cloud here represents the connections between these 5 computers. There may be cables in here. I'm just hiding that detail. So let's say this is the local area network of one organisation here in Thailand. And of course in other organisations across the world they have their own internal networks. So some other organisations, say in the US, they build their own network. Now this is before the internet was popular and before they connected with each other. They build their own network, connect their computers together just for internal communications. You can only communicate with people inside your LAN, for example. They may use different technologies. Okay? So the technology used to connect between these can be different from what another organisation uses. Their organisation will choose the best technology for their purposes. This may be Ethernet, this may be some old technology, some token ring network or some other technology to connect inside their LAN. I'll just label them, okay, we'll say that this network is using technology A and this one B. They're not connected, they cannot communicate with each other. That is, only these five computers can communicate with each other, and the ones in network B can communicate with each other, but not between the networks. They're not connected. So, and there are other networks in other organisations that will maybe use separate technologies. Of course, what we'd like to do is allow the computers on network A to be able to communicate with computers on network B. That's desirable, and that's in fact what the internet enables us to do, to connect a computer on one local area network to a computer on some other network in the other part of the other side of the world. How do we do that? If we think about the layers using this technology A, where will I draw it? If I draw, let's focus just on this computer as an example. When I say this network is using technology A, in terms of layers, we can most likely connect that to the bottom 2 layers. The physical layer is using technology or protocol as part of technology A, and the data link layer. As are all the other computers here. This one, for example, if we draw the stack, inside a local area network, all the devices use the same physical layer technology or the physical layer protocol and data link layer protocol. Because recall that these 2 bottom layers of our stack are about communications across a link or over let's say if we connect all these computers together via cables, there are better ways to do it. You shouldn't draw those, that adds becomes more complex. But if we connect all those computers together in a mesh, then they can communicate with any other computer in the network. They all support the physical layer using protocol A and the data link layer using protocol A. In most cases, the physical layer and data link layer go together. They use the same standard. Not always, but in many cases, at least in this example. And similar, if I draw the stacks in network B, they'd be using physical layer protocol B and data link layer protocol B. So that all computers in network B can talk to each other, all the computers in network A can talk to each other, but they cannot talk to each other across the networks because they don't use the same protocol. This computer, if I draw the bottom two layers, physical layer B, data link layer B, even if we connect a cable or we had a link between this computer and the one in network B, currently they're using different protocols. To be able to communicate with between the two computers, you need to use the same protocol at each endpoint. So there's our problem. How do we enable computers on A to communicate with computers on network B? What's the solution? How do we make them talk the same language? Use the same protocol. Okay, so one solution, force every network to all use the same data link layer and physical layer protocol. Okay, this one was built using technology B, force it to change to A. That's not a good solution when, if you think 20, 30 years ago, or even 15 years ago, before the internet was popular, many organisations had their own internal networks. They chose their own technology. Requiring them to all change their network, to buy new equipment, to buy new PCs, or at least LAN cards for the PCs, is just not feasible. You should be able to enable organisations to choose their own technology inside their network, but still be able to communicate with people outside. So forcing everyone to use the same data link layer and physical layer is not feasible in practice, everyone across the world. What's another way then? Same if one person talks one language, Thai, and another person talks German, then to allow them to communicate, you can translate. So to allow computers using different protocols to communicate, we could translate between them. Let's say we get this computer to translate from data link layer A, physical layer A, to B. That is, what it receives from these computers is from technology A, and then it translates or changes it and uses a second protocol to connect. So that, in fact, we could imagine this computer talks two different protocols, one using technology A and one using technology B, so that it can communicate with computers over there. Now, the problem with that approach is that, okay, in this example, there are just two networks. Now imagine the hundreds of thousands of different networks across the world. The many different technologies used across the world, this one would need to be able to translate from A to B, from A to C, A to D, and to many other protocols. That becomes complex, the same as if I need to be able to translate from one language to all the other 100 other languages used across the world. That's very hard to maintain. So the approach that's used, and that's used in the internet, is to get all of the computers to talk a common language. So to communicate inside your LAN, use your data link layer and physical layer protocol that you choose. To communicate with people outside your LAN on the larger network, use a different protocol. And this is at the network layer, and the protocol used is the internet protocol. There are others, but the one we're focusing on is IP. That is, force the computers in here to support not only their local technology, but also the internet protocol. Same with the computers over in network B. Let's say we draw this computer. It must support the internet protocol if it wants to be able to communicate with someone on another network. If it wants to just communicate with people on its own network, it doesn't need IP. It just needs to support its own technology B. But if this computer wants to be able to communicate with someone on some other network, then it needs to support the internet protocol. So we use a different language, a common language amongst all computers. Within the LANs, use your own technology, but for communication across LANs and wide area networks as well, use a common protocol, and that common protocol is the internet protocol. How does it work in a bit more depth? All right, here's one network, A and B. Let's draw some other networks that connect them together. Network C has some computers, and then network, this is D, and it goes across. And this is still network D. That is, we have 4 different networks here, A, B, C, and D. And they all have some computers on them, but there is a physical connection between network A and network C. This computer, this device, has cables coming from computers in this network A and also cables going to computers in network C, this network here. If we follow the same structure, this computer needs to support the data link layer A and the physical layer A to communicate with computers on this network. And it also needs to support data link layer C and physical layer C to communicate with computers on network C. It doesn't support B, only the networks that it's directly connected to, it needs to support those technologies. Similarly, if we look at this computer, we're looking at the protocol stack for each computer or for a selection of computers. We can draw it. This computer has cables coming into it from network C. So it uses the protocol that is used on network C. We're just labeling that as the data link layer, whatever the name is, C, and the physical layer, PHY, C. And similar, this computer connects to network D. So it needs to support the protocols which are used on network D, which are the data link layer D and the physical layer D. I'm just using A, B, C, and D to represent different technologies. One could be Ethernet, one could be wireless LAN, one could be some token ring or ATM. Many different technologies are available in the real world. This is the computer here. And finally, this computer that connects to networks B and D must support both technologies. And to be able to communicate between any computer on any network to any destination, all computers need to support the common language or the common protocol IP. This computer supports the internet protocol. This computer, and one way we often draw it, is also supports the internet protocol. This one does, and this one, this computer. Computers that want to communicate with each other must use the same protocol. This computer uses the internet protocol. It can communicate to here, onto this computer, and eventually to this one, because they all support the same protocol. And in this case, IP, the internet protocol, is part of the network layer. Recall, the network layer is about communicating across a network, across a set of links. We're trying to get to something about addresses and why we have two different types of addresses. And you may start to see with communications within our local network, say network A, we use technology A, physical layer A, data link layer A. All these computers support technology A. And to communicate from this computer to another one, let's give them names. For simplicity, let's call this one A1, A2, A3, A4 and A5. 5 computers attached to network A. We can think of these names, or to be able to communicate with any of those 4 other computers, we need to know their address. If this computer wants to send a message to here, it would set the source address as A1 and the destination address as A4. So that, remember from our measures of effectiveness, so that we can deliver the data to the correct destination. So this is what we'd call a hardware address. It's an address associated with the data link layer and the physical layer. We call it a hardware address, but some other names you may see: a physical address, a data link address, even a MAC address. So we can think in general it's an address associated with both of these layers, or one of these 2 layers. Sometimes the physical layer or the data link layer. In fact, there's also the data link layer contains what's called a MAC layer. But a hardware address is okay as a name. So the blue ones here, A1 through to A5, are hardware addresses of these 5 computers. Similar, the computers on network B have hardware addresses associated with the technology they use. Let's say this is B3, B2, B1, B6, B5, and B4. On this network, we're using technology B. On the other network, we're using technology A. The address formats may be different. Different technology, the structure of the addresses, the length of the addresses, how they are formatted may be different. It's up to the standard as to what address you may use. I've written them as numbers and letters, but this may be in fact a 48-bit address, and this over there may be just a 16-bit address. They may be completely different types of addresses, depending upon the technology used. A1, or actually we've got A1 wants to talk to computer B3. But A1 knows nothing about the technology that computer B3 is using. It's a different technology. A1 only talks technology A and also the internet protocol. And it knows nothing about the address structure used by network B. So it doesn't in fact know that this computer has address B3. What we do is we have a second address, an address associated with the internet protocol, called a logical address, or sometimes a network address, or specifically an IP address. So this computer has an address, a hardware address A1. In addition, it has an IP address. Let's call it IP. I'll just give some random numbers. IP23. This computer also needs an IP address. And the other computers would have IP addresses as well. This computer, A4, has an IP address. And we'll come back to those ones in the middle. B3, because it supports the Internet Protocol, would also have an IP address. For our source computer, A1, to communicate with the destination computer, B3, it doesn't use the hardware address, it uses the IP address. Source is IP23, destination is IP204. And those numbers I chose are just random numbers for this example. So to communicate with someone who's not on your network, you need to know their IP address. To communicate with someone who's on your network, you don't need their IP address in theory. You often will use it, but you communicate directly using the hardware address. But anyone outside your network, because they may use a different type of address, a different technology, you use the Internet Protocol and IP addresses. So all of these devices have a second address, an IP address. Doesn't matter what the values are here, as long as they're unique. In any one network, all the devices should have a unique address. Because if we want to deliver the data to the correct destination, then if I say the destination is IP204, but there are two computers on the internet with that same address, which one does it go to? So the address should be unique on the network. So across our entire network here, our internet here, we should have unique IP addresses. Inside a local network, we should have unique hardware addresses. Let's look at this device. This device is in fact connected, here's our protocol stack, to two networks, A and C. It will have two hardware addresses, A4 and C1. An address for talking on this network and another address for talking on network C. And in fact also have two IP addresses. As will this device. Two hardware addresses and two IP addresses. And this B5 would also have an extra hardware address and IP address. Those B5, this one, and A4 are special devices in our network. We often call them routers. We may have mentioned routers before. We'll look at them in later detail after the midterm. But they have a special role of delivering the data from the source to the destination. What are we missing? So now, this computer wants to send something to the one on their destination. This is our source host. I've drawn the stack, just the bottom three layers. In fact, above that we have a transport protocol and an application protocol, depending on what application we're using. Last week we saw an example of using HTTP and TCP. So I generate some data. It's processed by the application and transport protocols. And then IP goes to work. Inside the IP packet, if you can remember from last week, there is a source address and a destination address, where the source address will be IP23 and the destination will be IP204. Running out of space, but the source and the destination The source is this computer and the destination is the one on the far right, which I think is 204. Then pass the IP packet to the data link layer, does its processing, and then the data link layer and the physical layer use the hardware addresses to communicate. In fact, if we look at the frame from the data link layer, it also has a source address. I'll draw it down here so I have space. For the data link layer packet sent by this computer, what's the source address? The data link layer packet is sent. It contains a source address and a destination address. What do you think the source address is? What value? Anyone? The colours may give you a hint. Which computer is sending this packet? A1. A1 is the data link layer or the hardware physical layer address. A1 is sending this packet across this network. The source address is A1 here. What's the destination address? It's sending it on this network to A4. So the destination is A4 here. So note those two different types of addresses, the IP address used at the network layer and the hardware address used at the data link or physical layer. The IP address identifies the source and destination on the entire network, or with what we'd call on the internet. The hardware address identifies the source and destination on the local network or across the link. So A1 really needs to send to A4. To reach IP204, we need to send to A4. So we send something to A4. A4 will receive it. The destination is A4. This is the stack for A4. A4 receives it, processes it, and then sees the IP address. Destination is 204. This computer is not 204. 204 is somewhere over there. So this computer will then send it to the next computer. We don't have a name for it. Let's give it one. C2. Would send it to C2, which would then see, okay, destination is IP 204. We'd need to send it on to here, which would be, let's call it D2. This computer would receive it. Destination is IP 204, sends it to B3, which is indeed IP 204. So the addresses are used differently. The IP address is used for communications across an internet, and the hardware address is used for communications within a LAN or within a wide area network. And in practice, all devices have both. Or all devices connected to the internet have both addresses, a hardware and IP address. Some devices have multiple instances of those addresses. Those devices that connect networks together have multiple addresses. So we have two types of addresses. One thing that this example doesn't cover is that, in fact, a computer has an address for each interface. Not just for the computer itself, but each interface on that computer has an address. We said last week, my laptop has an address, or can have an address for its wireless LAN interface, for its Ethernet wired interface, for its Bluetooth interface. So not just per computer, but per interface on a computer has a hardware address and potentially an IP address. We've gone a little bit too far in how IP works in this example. That is, we're going to return to how do we get the data to this router and to this router and so on to the destination after the midterm when we look in detail about the internet protocol. The main point here is that we have two different types of addresses, the hardware address and the IP address. A hardware address identifies an interface on a local network. An IP address identifies an interface, and more generally a computer, on the internet. Any questions about the differences between the two types of addresses? What this allows is that in the internet, if everyone supports IP, it means that SIT can use one technology inside their LAN, technology A. Someone over in another country can use a completely different technology inside their LAN, technology B. So long as they both support the internet protocol, they can still communicate with each other. So there's no requirement that every network, every computer must support Ethernet, or every computer must support wireless LAN. They can support different technologies across the world. So long as they support IP, they can communicate with each other. We'll see some more examples a bit later. We saw an example last week. My laptop had a hardware address and an IP address. It's not that easy. There are more addresses. These hardware addresses and IP addresses identify interfaces on a computer. On my computer, I may run multiple applications. On my laptop, I have a web browser running, an instant messaging client, an email client, a Skype client, multiple applications that want to communicate across the internet. When someone sends a packet to my laptop, they send it destined to my IP address, which identifies really my laptop. But then within my laptop, where does that packet go to? Does it go to my web browser, my instant messaging application, email client, or my Skype application? Which application does it go to? Well, we have different types of addresses to identify applications. Port numbers, or sometimes called a transport address, because we associate port numbers with the transport layer, or a, well, less common, a service access point, but we will call them port numbers. So each internet application running on my computer has a port number, an address that identifies that application. My web browser may have some port number associated with it. And I just chose a random value. And if I'm talking to a web server on this computer here, I haven't drawn the stack. There's a transport layer and an application layer. The web server has a port number associated with it, which is normally what value? 80. You would have seen it, or you've come across it in some cases, I think. A web server normally uses port number 80 to identify itself. A web browser normally uses a random port assigned by your operating system, but a web server port 80. When this computer receives the packet from my web browser, that packet contains the destination port address. Destination port address will be 80. So this computer that's running a web server, an email server running on port 25, an SSH server running on port 22, and others, when it receives a packet from my web browser, the destination port should be 80. So when it receives the data, the computer knows deliver the data to the web server, not to the email server or SSH server, or not to some other application. Deliver it to the application using port 80. So port numbers allow us to have multiple applications on a computer and communicate between them at the same time. The fourth type of address you'll come across may be classified as user-friendly addresses or application-specific addresses, like email addresses, domain names. Skype may have a specific type of address format for their application. Some instant messaging applications have address formats, usually follow email addresses or login names. But different applications may have their own address format. Usually in some user-friendly format, something that I can remember as a human. Remembering random port numbers, IP addresses, hardware addresses are generally not human-friendly, they are for the computer. So really 4 types of addresses. From the bottom, hardware, IP addresses or logical addresses, transport or port addresses, port numbers, and at the top, application-specific or user-friendly addresses. And the user-friendly addresses normally map into some IP addresses or some port number. The structure of hardware addresses, of IP addresses and port numbers we'll cover when we cover individual protocols. We'll see some examples through the course and another one today, but the exact format, how long is an IP address? We see from the slide before is 32 bits. What do those 32 bits represent? How are they chosen? That's something we'll cover later. Same with port numbers. You can try these on your own computer. They work on Windows, Mac or Linux. ifconfig on the command line, either any of those operating systems shows you the configuration of your interface, including your addresses. In Windows, it's ipconfig. And other programs that work on the command line show you information about your network interfaces. The mapping between IP address and hardware address, ARP, the mapping between domain names, www.google.com, and the IP address is using NSLOOKUP, and some statistics about your network, netstat. They all work on Windows, except it's ipconfig. We may see some more examples of those programs in some later lectures. That finishes us on addresses. So the main point, 4 types of addresses. Understand the differences between them. We'll learn about the structure as we go on. What's next? Last week we covered this example operation. We covered it with the Wireshark capture. We may have mentioned this sometimes. Where are these protocols implemented? Well, an approximate classification of where they're implemented in a computer is we can say that the application layer protocols are implemented normally in applications, in end-user applications, a web browser, an instant messaging client, an email client. They may implement the application layer protocols like HTTP, SMTP and others. So the application layer protocol is really in applications on your computer. I say here user processes, they are not part of the operating system. The transport and network layer are normally part of the OS. So when you have an OS on your computer, it includes some software for TCP, IP and other protocols within these 2 layers. That's part of the OS. The normal user, the end user, normally doesn't have any control over them. No need to. That's part of the OS to manage them. Data link layer and physical layer normally in hardware and what we call a network interface card. Now, it may be a separate card that you plug into your computer, or it may be a chip on board the motherboard, but referred to as a NIC or a network interface card. It's not always this case, but it's in the computers that we see, it's commonly that case, that separation between implementation. So if you have a Linux or even a Mac operating system, most likely you can find the source code for the Internet Protocol. So you'll find the C files. It may not be installed on your computer, but you can find the C source code, written in C normally, that implement IP and TCP and other protocols. If you have Firefox, because it's open source, you can find the source code that implements HTTP. Any questions on addressing or layers? The next part, the remaining part, is something slightly different before we move on. Any problems with the quizzes, the last two quizzes? Maybe there were some words in the last two quizzes that we hadn't quite covered. For example, I look back on that, there was one question was about a network interface card. Well, that may have been difficult to cover or to answer if you didn't know what acronym meant. But we're catching up on those quizzes. The last part of this topic, and it's somewhat different from what we've talked about in the past, is what different types of applications do we have in the internet, and specifically, how do we measure their performance? As computer scientists, as IT professionals, we often care about the performance of our network or the performance of our application. How do we measure that? First, what's an internet application? Well, a simple classification, a standalone application has some user interface normally, graphical, command line, but some interface for the user, and the application logic, the code that does what the application should do. You write a spreadsheet application that has some interface and some code that does all the calculations and does all the things that a spreadsheet needs to do. Okay, that's a standalone application. A networked or a distributed application works by communicating between instances of that application on different computers. So we usually have some user interface, the logic that does what the application needs to do, and also some mechanisms to communicate. So web browsing. Web browsing is enabled by two instances of web browsing or a web application, a web browser and a web server. They both have some user interface, they both have some logic, how to process HTML and so on, and they both have some ability to communicate, to send packets using HTTP in this instance. So that's the difference between, say, a standalone application that just runs on one computer and a networked or an internet application that works by communicating between instances of that application on different computers. What types of internet applications do we have? Well, there are many different internet applications. A broad classification is we can say that some are the traditional data-based applications or internet-based applications. I say data-based in that they are about exchanging files, whether it's a file or an email, which is just a file, or a web page, or exchanging commands. So file transfer, web browsing, SSH to securely connect to another computer, databases, many business applications to communicate within a business, what we'd call traditional internet-based applications. In these applications, we care mainly about accuracy. Remember our three measures? Delivery, we always care about delivery. That is, if I send something, it must reach the correct destination. Delivery. Accuracy, if I send some data, what is received should be an accurate reflection of what was sent. And in these applications, accurate means 100% the same. Send an email, the received email must be exactly the same as what was sent. The other types of applications we sometimes call multimedia or real-time applications. Examples, streaming of audio, of video, watching YouTube, where a server is sending video to your client. Interactive video and voice, a voice call, Skype, using MSN to make a voice call or a video call. Gaming even, where you're on a multiplayer game, an online game, where you're sending information between each other's or via a server to everyone's game to know where the other person is, to know what they're doing. Collaborative applications like viewing other people's desktop and so on. In these applications, timeliness is usually more important than accuracy, or at least just as important. That is, getting the data from source to destination should happen in a small amount of time. If it's too long, then the application will not work well. A voice call, too long, normally it's about less than a second. Normally in the order of 500 milliseconds becomes too long. That is, to get data from one computer to another, from a source to a destination in a voice call, a good time that gives good quality voice communications is in the order of tens of milliseconds. If it takes 1 second or 2 seconds to get what I say to the other person, if you're having a voice call, then from the other person's perspective there starts to be some delay. And they are waiting for you to say something when you've already said something. And you cannot converse very well if there's a large delay. You may have noticed that if you, even on landline phones, talking overseas, on Skype sometimes, if it's a bad connection, if there's a large delay, then it's very hard to have a conversation that flows well because of that delay. So timeliness is more important for these applications than the traditional internet-based applications. The last thing we want to do is look at how do we measure the performance. You need to build a network. When you go get a job, one task you may have is to build a network for a company, for a small organisation. One thing that the users care about is performance. What are the measures of performance? There are many, but the main ones we will see in this course. Bandwidth. This is a measure related to the physical signals that are sent. We will not try and explain it here because the next topic explains it in depth. It's the range of frequencies that a communications channel can pass. If I plug this LAN cable, which really has some copper wires in it, if I plug it into two computers, then the signal, the electrical signal sent through here has a range of frequencies. And typical for a LAN cable is a range of about 100 megahertz. We can say the bandwidth when I'm using normal LAN communications across this cable, the signals have a bandwidth, that is, they range in frequencies from 0 or 1 hertz up to a maximum of 100 megahertz, a range of 100 megahertz. That's bandwidth, measured in hertz, or some multiplier of hertz. We'll see that's important when we look at how signals are transmitted. Generally, the larger the bandwidth, the faster you can send. And the faster you can send is about data rate. When we're talking about digital communications, we're talking about how many bits per second can we send across some channel or across some link. When I connect my two laptops together using this cable, the signal occupies a bandwidth of 100 megahertz. What's the data rate that I can send across this cable? Anyone want to guess? 1 gigabit per second in some cases? 100 megabits per second in some cases? It depends upon the LAN card in your computer. Most computers today will support a LAN card that has a data rate up to 1 gigabit per second. just an example. So a LAN card in your PC and your laptop, the older cards supported 10 megabits per second. Almost all today support 100 megabits per second, and most in fact support 1000 megabits per second, or 1 gigabit per second. So that's the data rate supported by the technology, by the transmitting device, the receiving device, and the cable, the media. Even though this is 100 and this is 100, that's a coincidence. There's no, they're not necessarily the same. They don't have to be. You see, we can even send 1000 megabits per second across a channel with a bandwidth of 100 megahertz. Let's connect. What I'm going to do is connect my small laptop with another laptop via this cable. So just plug it in to the LAN cards, if this laptop works. I'm going to disable the wireless on my laptop, if I can see. And plug the two computers directly into each other. So my network is the simplest of networks you can have. Two computers connected directly together. And let's look at some of the, let's make sure it's plugged in. And what I'm going to do first is, on my laptop, the blue laptop, I'm going to configure the network interface card and give it an IP address. Because my network just has two computers, I need to manually assign an IP address. One student, you don't have to know how this works, I'm just going to quickly do it. I'm going to configure the interface ETH0, my LAN Ethernet interface. I'll give it an IP address, 192.168.1.30, and some other information which we'll ignore for now. And up means I'm going to turn it on because it was previously off. I wasn't using my LAN card. It needs my password to do this. So, and I've done the same for the other laptop. Both LAN cards are on, they're connected together. What characteristics of those LAN cards do we have? Well, we can look at, there's a tool to look at the Ethernet LAN card capabilities. Some of it we'll recognise, some we won't. First thing we recognise, my Ethernet LAN card is using a speed of 100 megabits per second. That's the data rate. The data rate supported by my laptop LAN card is 100 megabits per second. If I looked at my other laptop, it in fact supports also 1000 megabits per second, 1 gigabit per second. But this is an older laptop. Although the terminology may be strange, from the numbers we'll recognise that this LAN card supports 10 megabits per second and 100 megabits per second. So it in fact supports both of these, and it will choose the highest that both devices support on the link. The other laptop supports 10, 100 and 1000. My blue one supports 10 and 100. The highest that is common is 100 megabits per second. So that's the data rate for my link. Other information I think is not, this gives us some information about the cabling used, twisted pair. The copper wires are twisted together. One thing we'll cover shortly, either today or tomorrow, is just remember it's full duplex. We'll explain that later. And the useful thing is that the link is detected, that my laptop knows that there's someone at the other endpoint. So that's the data rate. So we care about the data rate because the higher the data rate, the more data I can send across the link within some period of time. What I'm going to do now is send some data from, in fact, I'm going to download a file from one laptop to the small laptop. And we're going to measure how long it takes to download that file. The big laptop runs a web server. So I'm going to use a web browser to download a file from the web server. I know there's a file on the web server, and I know on the web server that the file size is 100 megabytes. Let's draw this network. On this laptop, I have a web server, and I have a file on that web server, and I've created it before. It's called meg100. It's just a binary random file, and it's approximately 100 megabytes in size. I have a 100 megabyte file there. I'm going to use my web browser on here to download that file. But because I want to measure the speed and give a number output, I'm not going to use my graphical web browser. I'm going to use a command line web browser. It's not really a web browser, it's just a file that downloads something from a web server. It's called wget. And I type in the address of the web server. And I know the address of this computer, the IP address, because I said it before. And I know it's in the ITS323 directory. I hope it is. And that's the name of the file. All this is going to do on my blue laptop is to send a request to the web server at computer 192.168.1.20, the large one, asking for the file meg100.bin. And then it's going to send the file, the 100 megabyte file. How long is it going to take? Calculate how long it's going to take. You had a question in the first quiz about this. How long is it going to take? About, all right, correct? 800,000. Get your units correct. 8 hours. What are the units? 8 seconds. Okay. Why? 100 megabytes. Note the uppercase B multiplied by 8. It's 800 megabits. Is the size of the file. My data rate we saw before is 100 megabits per second. My link supports 100 megabits per second. I can send 100 megabits per second. I have 800 megabits. It's going to take 8 seconds. Let's try. Let's hope it works. It's downloading. It's downloading the file. And the reason I'm using this is it will report how long it took. 8.6 seconds. You were wrong. Okay, close. More importantly, this gives us the... So 8.6 seconds. It's not exactly 8. Why is it different? Why is it slightly longer than 8? All right. In fact, it's not exactly 100 million bytes. There's actually this extra 158,000, but that's only a small thing. Let's look at the calculation. The software actually reports the performance. And this is what we'll call the throughput of the link, of the download. 11 megabytes per second. So we'll say, in this case, the throughput is 11 megabytes per second, which is equivalent to 88 megabits per second. Times by 8. How do they get that? 100 megabytes divided by 8.6 seconds is approximately 88 megabits per second. Not our 100 megabits per second, but slightly less. That is, it didn't take 8 seconds, it took slightly longer. And we call the actual time it took, or the actual rate at which the data was transferred, the throughput. The data rate is the maximum speed that we can send across the link, 100 megabits per second. But if you remember from last week, we have all these layers involved. We have some data, we add a header, some more headers and so on. And the protocols do things like send data, send back an acknowledgement, and do many other things. There are many what we call overheads. There are some time when we're not sending data, but sending either header or sending nothing. So the throughput is the measure of the real rate at which we transfer user data. The data rate is the measure of the maximum speed at which we can send bits across the link, 100 megabits per second. But because we have some overheads, in this case the overhead contributed about 12 megabits per second, we get a throughput of 88 megabits per second. That is, we don't get the full 100. Maybe thinking of this 12 megabits per second is not a good way to think about it. But there's some overhead. There are some things we're doing when we're either not sending the file. For example, we're sending header on packets. That's not part of the file. Or we're not sending anything. And it depends upon the individual protocols. But in practice, there's always some overheads involved of sending that data. And in this case, the throughput is the measure of the rate at which the file was transferred, 88 megabits per second. You'll notice that even more when you connect to a Wi-Fi network, wireless LAN. Most Wi-Fi networks support a data rate of, say, 54 megabits per second. But you'll never get that when you download a file. Your throughput, when you're downloading a file, because there are many different overheads, may be less than 20 megabits per second. And it may vary over time. So data rate is the maximum capacity of our link. Throughput is the rate at which real data is transferred across our link or our network. Throughput is always less than data rate. Data rate is normally a characteristic of a device or a link that we buy. When I buy the laptop, I know it supports a data rate of 100 megabits per second. The throughput depends upon the application I'm using, the software I'm using, and what I'm actually using that software for. That's something we cannot predict when I buy the laptop. When I'm using my web browser, maybe the throughput is 88 megabits per second. I use another piece of software, it may be 89 megabits per second, or 80 megabits per second. I don't know. It depends on different factors. But the data rate is usually fixed for a technology. We care about both. Well, in fact, we mainly care about throughput, but we cannot always predict or calculate what throughput will be in advance. So we also care about data rate. Think of data rate as the upper limit, the capacity. Throughput wants to approach the capacity. It never will, but we want to get that as high as possible. Throughput, the amount of data successfully delivered to the destination. Still measured in bits per second, but is a measure of the real data that gets delivered. We'll do some calculations shortly. Last, or two more performance metrics. The last one we'll focus on or mention today is delay. How long does it take to get a bit from source to destination? We need to spend some time on that to do some look at the details of delay. Before we do that, let's give an example on my computer. I want to know how long it takes to get one packet from my blue laptop to the other laptop. And in this case, get one response back. And a program you may have used is ping. And I'm going to ping this other computer. Maybe I'm not. Why not? Because my link has gone down. That was unsuccessful. My computer's gone to sleep. That's why. Let's try again. Make sure. Clear. Make sure my address is set. I'm going to now ping from one laptop to the other. So what ping does, and I'll just cancel that so we see what the response is that ping sends one small packet from the source to destination, and the destination, when they receive that, sends back a response, one packet in response. And it does that every second. So what ping reports is every second it prints a line, and it shows the time it takes to get there and back. This time, 1.06 milliseconds, and then 0.562, 0.617, and so on. So about half a millisecond, or about 500 microseconds. That's the time to get one packet there and back. So to get there is about half. It's called the round trip time. And it gives some other statistics. So in this case, the delay to get there is about 250 or 300 microseconds. To get there and back is about 500 or 600 microseconds, or 0.5 or 0.6 milliseconds, as reported here. That delay depends upon different factors. We're not going to try and explain them today. We'll do that tomorrow, because we'll do another example today. In the last 10 minutes, I think, let's go back to let's look at data rate and throughput with an example. And the example is from an exam, from a quiz 2 years ago. You have a read, then we'll go through it on the board. There's another example in your handouts, which is more detailed, but we can go through this one a bit faster. And it's eventually going to give us some comparison between throughput and data rate, but it's also going to show us some other information as well. In this example, and it's a very simplified example just to illustrate some points, it's not a real case, we have a protocol architecture which has 2 layers, not 5 layers like TCP/IP, but 2 layers. Let's give them a name, the application, or even just data link layer and the physical layer. 2 layers, simple. And as we saw last week, the protocols at each layer add some header to the data that we generate. So in this case, the protocol at the top layer adds a 20-byte header. So if we draw our data, we have an application that generates data. In this question, the data generated by the user is 10,000 bytes in length. So we have 10,000 bytes here. The protocol at the top layer goes to work, processes that, and one thing it does is it adds a 20-byte header to that data. So if we draw that, we take our 10,000 bytes and add a header to the front of that. So in fact we have currently, first we have 10,000 bytes of data and we add a 20-byte header, so we now have 10,020 bytes in total. And then that 10,020 bytes is sent to the next layer, the bottom layer in our simple case. And the bottom layer does something here to try and improve performance of the data transfer. It limits the amount of data it will send at any one time across the link. It limits it to 3,000 bytes. So it says that the bottom layer breaks the received data. What did the bottom layer receive? It receives this. It breaks that into segments that are no larger than 3,000 bytes. So let's do that first. Take this 1,020 bytes and break it into segments. That is, break it into 3 chunks, each no longer than 3,000 bytes. How many chunks or segments do we have? 4. We have 10,020 bytes. Break it and let's try and draw it. Let's use black. The first will be 3,000 bytes, then another chunk, I'll draw it next to each other, will be 3,000, then another 3,000, and the last segment will be 1,020. Oh, 1,020. We've got 10,000. So this protocol has a rule. I'm not going to send anything larger than 3,000 bytes. So if I receive more than 3,000 bytes from the higher layer, I'm going to break it into segments. So we now have 4 segments. 3,000, 3,000, 3,000, 1,020. A smaller one at the end. And for each segment adds a 10-byte header. So let's draw them. 10 bytes plus the 3,000, and the second segment will be 10 bytes plus the 3,000, and the last segment will be a 10-byte header and just 1,020 bytes of payload. Not very close to scale, but we now have 4 segments that are going to be sent by the bottom physical layer. And it sends them one after the other. It sends the first one and then the second, the third and the fourth. It sends that across the link. So it sends it out of the computer and across to the destination. How many bytes does it send across the link? How many bytes does this computer send across the link? $10,060. Just add up those values. We have the original 10,000 plus the first 20-byte header, which is in here, plus the 4 10-byte headers. So the total amount that's transmitted is 10,060 bytes. The total amount of user data, the original data, is 10,000 bytes. Now let's, in fact, the question that we're going to answer first is slightly different from there. let's imagine our link has a data rate. What did I set it to? The link here has a data rate of 1 megabit per second. So that's how fast we can send across the link. We've got 10,060 bytes, or multiplied by 8, 80,480 bits to be transmitted across our link. We transmit at 1 million bits per second. How long does it take to transmit all of them? 0. What? Seconds. Let's be more precise. 1 million bits per second. An easy way to calculate in your head, 1 million bits per second is the same as 1 bit per microsecond, or 1,000 bits per millisecond. 1 bit per microsecond, we have 80,480 bits. It takes, so the time it takes is 80,480 microseconds, or 80.48 milliseconds, or as the answer, 0.08048 seconds. All of those are correct. But the way I would calculate, okay, 1 million bits per second is the same as 1 bit per microsecond. 80,480 times 1 is 80,480 microseconds, or 80.48 milliseconds. We have 10,060 bytes to transmit at some speed. It takes some time, 80.48 milliseconds. Now, at what rate was the real data transferred across the link? The real data, the user data. As a user, when I'm downloading a file, I don't care about all the overheads. I care about my data, how fast that's transferred. That's the throughput. What's our throughput in this case? Where can we write it? Over here. Throughput is the rate at which the real data, the user data, is transferred. How much user data do we have? 10,000 bytes, or 80,000 bits. How long did it take? One of those three, which one was 0.08048 seconds. 80,000 divided by 0.08048 seconds gives us the throughput. And I need a calculator. It's about approximately 994,000 bits per second. You can get it more accurate with that. Or 0.994 megabits per second. Our data rate of our link was 1 megabit per second. Because of the overheads introduced by the protocol stack, the throughput in this simplistic example is slightly less, 0.994 megabits per second. Or in other words, we're 99.4% efficient. I've paid for a 1 megabit per second link. I'm using 99.4% of it to send my data. The rest is for overheads. change 3,000 bytes to 300. In this first question, the maximum size of each segment was 3,000 bytes. Change the maximum size to 300 bytes. And find out what the throughput is when you change that. And think about what's going to impact upon throughput across the same link. We're out of time for today. What you'll do is attempt that by changing 3,000 to 300 and see what happens when you divide into 300 byte segments. How many segments? I think if you can get 34 segments, you'll be correct, and then work out the overheads and find the throughput in that case. We're finished for today. Tomorrow we'll give you the answer to that, and then we'll look at delay, what impacts upon delay.